Greetings. This is a lecture about the mathematician Ramanujan, who grew up dirt poor in in India, managed to find his way to Cambridge to Professor Hardy, with whom he worked, producing beautiful mathematical expressions that we'll do a quick survey of in this lecture. 2016, there was a major motion picture about his life, The Man Who Knew Infinity. If you want to see something for free, here's a YouTube link that leads you to a documentary about 1 hour, which has little of the romantic content that the motion picture has, but it does show the community he grew up in and what his life was like as a young person prior to going to England. As you can see, his life was short. He struggled with a number of issues once he got to England, but his notebooks reveal a intuition about mathematical structures that are still being studied today. So in this talk, I'm not going to worry about his life so much, only briefly, but we'll look at some of the mathematical ideas he worked on. So I've already said this. He was born in poverty. He somehow found math books left behind when an older student moved on, and he mastered those books quickly, including developing proofs for nearly 5,000 formulae that were in a reference book. He did this without any formal training. Once again, here's the link to the YouTube reference. So this is the kind of thing that he was really good at, and the story is that he produced this masterpiece at the age of 4 and confounded the elders who knew something about math. And he said to them, well, what does this structure represent? See, it's a continuing square root system. The square root of 1 plus 2 times the square root of 1 plus 3, and so forth. And they were stumped, but here's what he was able to show, that pick any one of these things and it can be partitioned. For example, 1 plus 2 times the square root of 1 plus 3 times 5. This is 16, and the square root of that is 4. And this 5 is the square root, of course, the square root of 25. So you see, this is an equation where 1 plus 2 times this root is equal to 1 plus 2 times root 1 plus 3 times the square root of 25. So he saw this kind of pattern, and he worked the other direction. He said, well, 3 is the square root of 9, which is the square root of 1 plus 8. And 8, so that can be expressed as 1 plus 2 times 4, and 4 is the square root of 16. And the square root symbol should extend all the way. Sometimes it does. So you get this, and 16 is equal to 1 plus 3 times 5, and 5 is the square root of 25. So when you start building this thing, you end up ultimately with this structure here. So the answer is this big messy thing here is equal to 3. If you start with 3 and work through it, and if you had the patience, you could build a big long version of this, and you would see this beautiful structure all equal to 3. Interesting. He also had these kinds of things just in his mind, many of which never got proved, but which are proved in the sense that they're derived from from fundamental principles of mathematics, but they can be tested mathematically, and it turns out that they are true. This was a great surprise to Hardy, who when he first saw Ramanujan's equations thought they just were the scribbles of a madman. But Hardy had one of his students check something like this, and sure enough, if you do this square root of -1 plus the square root of 2, it is equal to this infinite series, and if you do it for enough terms, you end up with something very, very close to this. And you can see once again the beauty of these structures, the fact that, for example, these exponents go -2 pi, -4 pi, -6 pi, and so forth. A pattern emerges. Ramanujan also worked on what are called Bernoulli numbers that have this kind of behavior. And he was in love with continued fractions. So we see here a thing you can calculate on any calculator. The square root of pi e over 2 has this, once again, beautiful artistic structure, which, you can imagine an average person finding this part and having some idea that that was a useful thing. But here, Ramanujan added this piece. And it has been shown that if you work essentially an infinite number of terms of these series, you get exactly this. Really unexpected result. Here's another one of his continued fractions. And another. This is, there's now a branch of mathematics, I guess it's in number theory, where these continued fractions now have a formalized notation that you see here. A mathematician seeing this will visualize this. That is, you start with this 3, and there's a semicolon here to indicate we're going to put a plus sign there, and then continued fractions with the 7, 15, 1, 292, and so forth are separated by commas. So that's an interesting thing. Could talk a bit about the golden ratio, which is commonly discussed in art. This is something the ancient Greeks understood, that there's a sort of a graceful appearance to a rectangle that has this property that if you take a square A side, and have an additional element of increment B, so this is A plus B, and this is A, and we do a ratio, that is, what's the ratio of this dimension of the rectangle to this dimension? That's this. And insist that B is selected so that the ratio of A to B is equal to that ratio, that first ratio. And we do some arithmetic here. And using, you'll recognize something if you remember your high school math, you'll remember the quadratic formula. You can do a solution to this and get this result. And now we're interested in the ratio of A to B, which is also the ratio of this long side of the rectangle to the short side. And a little calculation reveals that that's equal to 1.618. And a lot of computer screens these days have this kind of dimensionality, but the Greeks knew this. They had artistic thoughts in mind when they designed buildings. The Parthenon, for example, has this, if you look at the side of the Parthenon, has this property, the height and length are dictated by this. So we introduced that because Ramanujan saw another way to say this. He saw it as a continued fraction, which only includes the number 1, as you see here. So this ratio that we just looked at, namely this, phi, in this version Remember, well, this is what we calculated, but it can be expressed this way. So if you just look at the first term, 1, we get that. Then you have 1 over 1 plus and so forth. The question is, how do you do a calculation of this type? And a convenient way to do it is to stop the series and just put a number right here, any number. I'll show you that on this page. So if we put the number 2 right here, and we use this algorithm, we put a 2 and take its reciprocal, we get a half, and add that to 1, and we get 1 1/2. And take the reciprocal of that, and you just keep doing this, and you can see the values oscillate. I'm trying to indicate this as a row. 1.5, 1.66, 1.6, 1.625, it goes down, it goes up, and eventually you get to 1.617 and approach the actual golden ratio is 1.618. So notice that the starting point in the series is not important. So if you start with, well, let's go back so you can see what we're talking about. Whatever number you put here is depicted by this row. If I put in 1.6 to start and do that iterative calculation, right here I get to the golden ratio to an accuracy of 8 places. If I started with the number 2, I still get to that same value, but it takes a few more steps. 5, 100, 2,000. It only takes a couple more steps and you get the right answer. So it doesn't matter what you start with. Here's some examples of golden ratio you see in art. Key points on the Mona Lisa produce this spiral. And there's the golden ratio. They produce this spiral that encompasses the figure. And here, if we just flip that spiral over and look at it, you'll see that there's a rectangle formed here. Here's the short leg and the long leg. And then right here, that rectangle has the same ratio. And then there's this rectangle, this one here, it goes like that. And this one, and a little tiny one. And the spiral, as you can see, is dictated by starting at this corner and going to that corner and that corner and that corner. If you follow it around, you get that spiral dictated by the golden ratio. So now let's go back to Ramanujan. Hardy is quoted. Lots of interesting quotes from Hardy about his first experience looking at Ramanujan's notebooks and saying things like, seemed scarcely possible, like this bizarre thing. It's, yeah, obviously calculus here. And that's as an infinite product. That's what this symbology means. So you take this structure and multiply it by this structure and just keep repeating that. And that integral is equal to this thing here. Engineers and mathematicians will recognize this as a group of gamma functions. These are properties of gamma function. That's a totally unexpected result, but it is now known to be true. Here's a power series that he conjured up. 1 minus 5 times a half cubed plus 9 times this thing minus 13. That's an infinite series, and it comes to 2 over pi. And similar kind of unexpected thing here, another infinite series with this nice feature, including the gamma function again. Here's a link that talks about these series. This formulation, it would be fun if I had done this without letting you see the answer, right? Whoops. So the way I present this to students is like this. Compute the first term of this series. So you have, this is just a number. And k goes from 0 to infinity, so we can start with k equals 0. You put a 0 there. You have to remember that 0 factorial is equal to 1. And then you get a 0 here. So you have 1103, and once again, 0 factorial is 1 to the 4th is just 1. And this is 0 here. And so you do this calculation, you get something close to 1 over 3. And if you now add, remember this is a sum, so if you now do the same calculation for k equal 1 and add that, and k equal 2, and so forth, and if you do it long enough, you discover that this bizarre looking creature is equal to 1 over pi. There's a discussion of this here. Let me move that a little bit. Partition functions. He was big into partition functions, so the number 4 can be expressed a number of different ways. These are arithmetic partitions, that is, 4 is a partition of 4, but it can also be expressed as 3 plus 1, 2 plus 2, and so forth. The number 250 has a partition number, that is, the number of ways that it can be expressed as a sum, and that the number of ways is enormous. Ramanujan created this approximation for the size of the partition function of any number. It's something easy to do in a calculator. For as n gets bigger, this becomes more and more accurate. How he got this, I don't know if anybody knows. I think the story is that when he arrived in England, he gave the cab driver at the train the address of where he was supposed to go, the rooming house or something. And the cabbie made a comment about the number 1729. Seems like a mundane number. And Ramanujan said, oh, no, it's the smallest number that can be represented in 2 different ways as the sum of 2 cubes. And here they are. He just knew stuff like that. And incidentally, 1729 is the product of 3 primes. And here's some additional history. If you're interested in that, you can read about it. Now we come to, in the next page, I don't want to talk about it I don't want to show it to you till I talk about it a bit. A result that Ramanujan developed on his own in India. He proved what I'm about to show you in 2 ways, and it's still a controversial result that causes consternation. If you want to have fun with this, if you go to your local bar, you can win some money with this idea, that the sum of all the natural numbers is equal to what? And I won't go through this. You can read through it, and if you want to get some details from me, write to me. The sum of all the natural numbers can be shown to be equal to minus 1 over 12, which seems crazy, because you can, if you sit down with your calculator and add up 1 plus 2 plus 3, very quickly you get an enormous number. But once again, you can show mathematically by 2 different techniques, one of them is depicted here, that sum, if you were patient enough to do an infinite number of sums, you would get minus 1 over 12. Here's some references to this. Here's a picture of the notebook, or perhaps a letter. Yeah, I know it's in his notebook. And his English is readable, actually, where he shows that the sum of all the natural numbers right there is equal to minus 1 over 12. So that's all I have to say about Ramanujan. He's what a character. And died very young, unfortunately. But references here to this curious sum, and by the way, there are many other sums of that type. And here are some references. So